Today, we're going to discuss how to use TPM 2.0, the Trusted Platform module, to secure your private keys. All right, so TPM is itself a pretty large topic, so we're going to just focus on a small part of it, which is the private keys. So high level, the Trusted Platform module is a secure crypto processor for many security applications, requiring strong device identity, data protection, and platform integrity. Some popular uses include device identity and attestation, secure boot to make sure your boot wasn't compromised, key storage, which we're going to focus on, disk encryption, and digital signatures, which we'll also touch on. So TPM 2.0 is the current standard, while TPM 1.2 was standardized in 2009, and we're not going to focus on 1.2. TPM 2.0 is the most common today. It came out in 2015. And here's the standard from ISO IEC. And this is just part one of the standard. So there's actually 4 parts. And part one, if we look at PDF, it's itself 278 pages. So there's quite a lot of documentation for the standard. All right, although many people think of TPM as a hardware chip, it actually has several different implementations. Yes, you can have a dedicated TPM chip. You can also have the TPM hardware integrated as part of your bigger chip, like an ARM-based SoC, system on chip. You can also have a firmware TPM, which is basically using firmware, which is like software that'll run in your CPU's trusted execution environment. Then when we're going to VMs, for example, AWS, you can have a virtual TPM, which can be provided by the hypervisor to try to provide some additional security to your virtual environments. And then you can just have a software TPM, basically an emulator of the hardware. And the software TPMs are largely most useful for development purposes. All right, let's take a look at kind of the high level of the architecture. Full screen, yep. All right, so just as high level, we illustrate the components of the TPM. We got the secure cryptographic engine. We got the non-volatile and volatile memory. And then we got some control subsystems. And the key components, we got the cryptographic coprocessor here in the center. There's a random number generator, key generation logic, and this is all kind of operating within a hardware isolated boundary. Then we have the configuration registers here, and we have command processing engine and policy enforcement. Policies are typically used for authentication. So we got the non-volatile memory. It's got your endorsement key, which is a unique factory installed identity key. It is used for attestation. We got the storage root key. Storage root key is not like an official designation, but it's often referred to as kind of the key that's the root for all other keys in your hierarchy. And then again, we got policies here, and we have non-volatile indexes where you can actually store keys. All right, let's start talking about key storage, since we're going to be focusing on private keys here. So first we have to talk about the authorization hierarchies. So there's 4 authorization hierarchies, each rooted in a different seed. So we have the owner hierarchy, where it uses the storage seed, and that hierarchy is used to store keys, and that's the one we're going to focus on. There's also an endorsement hierarchy. It has its own seed, endorsement seed, and it's used for identity and attestation. There's the platform hierarchy that has a platform seed that's used for kind of firmware level trust and control, and there's also a null hierarchy that just has some ephemeral keys and does not have a seed. One thing about storing keys, so like I mentioned, there is non-volatile memory here in the TPM. However, in practice, most applications avoid storing keys directly in the TPM. That's because the amount of this available non-volatile storage varies significantly between different TPM models, and it's often limited. Some TPMs only can store like 3 keys. So an application comes in, it doesn't know how much space it has in the TPM to store the keys. So instead, keys are typically generated and loaded temporarily into the TPM, and they're actually stored externally in an encrypted form, but they can only be used when loaded into the TPM. All right, so we talked about the authorization hierarchy, the owner endorsement and platform hierarchies. So let's talk about the key hierarchy, which is a different type of hierarchy just for keys. So there is the storage seed, and that's the start. This seed is a non-exportable hardware internal value that acts as the TPM's true root key. You can't access it, but you can use it indirectly. The storage seed, which is specific to the owner hierarchy, owner authorization hierarchy, it cannot be modified. So we have the storage seed. Then from storage seed, you can get a parent key. So parent keys could be stored persistently in the TPM, or they can be reloaded as needed. So the parent key is just used to encrypt or wrap one or more child keys. So in order to use the child keys, the parent key has to be loaded into the TPM. So you can create a parent key deterministically. So I think TPM does not randomly generate a parent key unless you explicitly ask it to. So that means if you provide the same hierarchy, like our owner hierarchy, which has the storage seed, you provided the same key template, things such as attributes, algorithms, and I'll have an example in a second here. And you provided the same authorization, for example, the same password or the same digital signature, then the TPM will create the exact same key every time. Because the TPM uses deterministic key derivation function. So this determinism means an application does not actually need to store the parent key explicitly. It can always recreate the parent key when needed. All right, let's go ahead and give an example. So we're going to be using TPM2 tools. Let me pull up a website for these tools. TPM2 tools. They can be installed on your Linux system. So I'll give an example here. So you would install it, basically sudo apt install TPM2 TSS. TSS stands for TPM2 software stack, and then you would install TPM2 tools to actually interact with your TPM from the command line. So I have these installed already. Unable to locate package. Let me look into that. Okay, so since I'm using Ubuntu, the TPM2 TSS is already installed. So I just need to install the TPM2 tools, which I already have installed. We can double check to make sure our TSS libraries are installed by just grabbing our packages for libtss2, and we'll see they are installed. Another thing you have to know is that in order to use the CLI, TPM2 tools, you either need to be root or a member of the TSS group. So in my case, I already made this user a member of that group. I have the TSS group here. Otherwise, I would need to type in sudo before every command. All right, so let's go ahead and create a transient primary parent key. So we're going to use the TPM2 create primary command. TPM2 create primary, and then we're going to pass it a whole bunch of parameters. I'm just going to copy and paste since it's faster than typing things out. All right, so we're going to have hierarchy owner. Owner is where the hierarchy that actually stores the keys. We're going to use RSA, SHA-256, and then we have the attributes here. We want this key to be specific to this TPM hardware. We want the key to be generated in the hardware inside. This is good practice to always use with auth, even if your authorization is a nil password. This is a parent key, so we're only going to be using it for decryption, and then restricted, meaning we are also not able to use it for anything else except decryption. And then we're going to save the context, which we'll reuse in future commands. So let's go ahead and do that. All right, we got an error. Okay, I looked into this and it looks like I needed an additional attribute called fixed parent. I didn't think that was required because I'm trying to create a parent, but it looks like it is required. Maybe it's because I'm using fixed TPM as well. So this is the command. I just added fixed parent here as well. So let's go ahead and run this, and we have our parent key. All right, so now, well, let me show you a code example. So this is how you do it from the command line. I'm also using this using a Go library. So I have, I'm using the library called Go TPM. I can show where it's at. It's right here. Google Go TPM. So I'm using this library in my code, and then there's these commands for creating. I have create a parent template with the attributes, RSA algorithm, and then it's simply called create primary to create the key. Okay, let's talk about next about the child key. So we have the parent key. So the child key is created under the parent key, which must already exist or be loaded. And so effectively the child key is encrypted by the parent key, and it's not usable on its own. It must be unwrapped and loaded by the TPM. Let's go ahead and create a child key using TPM tools. All right, I'm sharing the right screen. So in this case, I'm using the TPM2 create command, and what I have in this directory so far is I have the parent context. So let's go ahead and call TPM2 create. All right, so I'm passing in the parent context. I'm gonna use ECC with P256 curve, hash algorithm 256, and I have fixed TPM, fixed parent, data origin user with auth. So these four are the same as the parent. And then I'm asking sign to be able to sign with this key. Decrypt. I'm not sure why I have this. I don't think I need this actually, but let's just stick with what I have right now. And then it's going to output two files. It's going to output this child.pub blob and child.priv blob. Let's go ahead and run this. There we go. Let's look at the files. So we have these child blobs over here. Now, in order to be able to use these later, I need to load it into my TPM. So I'm going to go ahead and load it with the TPM load command. So what am I doing here? TPM load, I pass it the parent context, and I pass it the public and private blobs, and it's going to output a child context here. So let's go ahead and run this. It also gives me the name of this child, which can be used in some places, can be used like for verification, for example. All right, so we have the child context here. And let's take a look at the code. So in our code, we have, I create the child key. Here we go. Very similar. I have the type algorithm, these attributes, decrypt. I don't know if this is needed. Make a note for myself later. We create it, then we load the key into the TPM, and then we also save the context so it can be used later. Here we go, context save, execute right here. Okay, so we created the parent key, the child key. So we have to kind of mention persistence, right? I mentioned that we typically don't save the keys in the TPM itself due to limited memory. So the most common approach is to persist the child key outside the TPM. So you can store the public key and the private key, like you saw on disk. It can be in a secure database or in a file system. So when an application needs to use the key, it loads it into the TPM. So the reason that's safe is because the private key is always encrypted with the TPM's parent key. And so only the TPM with the correct parent key can use it. There's also a de facto standard for storing the TPM keys as in the ASN.1 format. So let's go ahead and pull that up. So there is this specification. It's a draft specification, but it's becoming kind of a de facto standard. Some tools such as OpenConnect VPN use this format for storing their TPM 2.0 key files. All right, let's talk about TPM signing. So signing is pretty straightforward. There's a TPM2 sign command that you pass your data or your digest, depending on what algorithm you're using, and then it gives you back your signature. So let's go ahead and do it. Let's go back here. Let's clear this. So let's create some dummy data. So we're gonna sign a string called hello world. Hello world. Put it into data in.raw. And then we're going to create a digest of this. This is typically what you do. You're signing a digest with most algorithms. I'm going to use OpenSSL, digest, SHA-256, binary, and we call it digest.bin. All right, so we have raw data in here, and we got our digest. So let's go ahead and sign the actual digest. So we're going to use TPM2 sign command, and we're going to be signing it with our child key. So we pass in the child context, SHA-256, digest. By default, it outputs a binary format, but here we're going to use this plain format because OpenSSL can actually read in this format for this particular algorithm, which is ECC2 with I think 256 curve. And this is going to be that signature using that plain format, and digest.bin, that is what we're signing. So let's go ahead and sign it. So now we have our signature here. So let's go ahead and verify it. But before we verify it, let's go ahead and create actually a PEM format of our child's public key. So there's another command, TPM2 read public, that we can use to get the child publicly in the PM format. So let's run that. And so let's look at that, child.pm. So where we go, PM format right here. And now let's go ahead and verify the signature. We're going to be using OpenSSL to verify it. Let's go ahead and look at this command. OpenSSL digest SHA-256-verify. We pass it the public key. We tell it it's PM format. We pass it the signature. So in this case, for this specific signature, OpenSSL knows how to read it. It may be possible if you're using some other algorithms that you might need to kind of reformat the signature if you're using OpenSSL to do the verification. And then we pass in the actual data, right? That is the data the signature is based on. Let's go ahead and run this, and we get the verified OK. And let's go ahead, look at the same example in the Go library. So TPM2 sign, that's what I'm calling it. So I'm just calling it sign, passing it the private key handle, the digest. That is the SHA-256 digest signature schema. So I'm using ECDSA here, passing it the hash algorithm. And it's pretty forward to do a signature. All right, I think that kind of concludes it. I did want to mention that this TPM2 has lots of documentations. I'm going to go ahead and show it. So they've got a read the docs page for TPM2 tools. So we've got all these different commands. For example, which one did I run? TPM2 sign. You can see there's lots of commands. So TPM2 is a big topic. Let's see, let's look at sign. And then we, through the switches, explanation of the switches, different switches you can use, things like that. So definitely a solid reference. All right, that's it for today. Thanks for watching.